We've been talking in this section about how derivatives can help give us information about the graph, and we've seen how first derivatives can tell us information about local mins and local maxes. Now we want to look at what second derivatives tell us, and that is the concept of concavity. So if the graph of f lies above all of its tangents on some interval I, then the graph is called concave upward. If the graph lies below its tangents, then it's concave down. So we've got two concepts here, concave up and concave down, that we are trying to understand sort of correctly. So if we start just sort of sketching in our graphs here. So these first couple that I have, at these couple of points, our graph is concave downward because the graph is lying below the tangent lines. And then we get over here and it's the same thing. But then at some point over here, that changes. And our graph starts to lie above our tangent line. And if we look at that, it might be kind of hard to tell where it's happening. It looks, because I'm not a great artist, it looks like it's happening somewhere in between here, that change is taking place. And so maybe I'll just pick sort of an arbitrary point here and say that between, or from negative infinity, by the looks of this, if this is going to go on, to this point A, we are concave down. And then, okay, as we keep going here, now we're going to be concave up again. And again, it looks as though that's going to continue for all of these things over here as well, that this is going to be concave up at these other points as well. So we maybe call this point B, and we'd have from A to B, we are concave up. So sort of in a general sense, that if we're thinking about this, this would be an example of, this is sort of the shape that we are looking for concave down. And because if we start drawing in any of these tangents, we've got that the tangents are lying above the actual graph, so that we'd say those are concave down. And if we were doing concave up, it's going to be sort of the opposite thing. So these would be examples, at least from A to B here, of being concave up or upward. I'll probably just say up or down and not use upward and downward. Now, I said that this is told to us by the second derivative, so let's look at that and look at some examples and see how that's helpful. So if f double prime of x is greater than 0 for all x in an interval, so when the second derivative is positive, then the graph is concave up, and when the second derivative is negative, it's concave downward. So we're going to go back to the couple of examples that we've already looked at. So we've looked at f of x equals x squared times ln of x, and we've taken the first derivative. And if we take the second derivative of this, as I did here, we just get 2 ln of x plus 3. And I'm going to treat this in very much the same way as I did before. I'm going to make a number line once I find these values where this equals 0, because if we look here, we differentiate between greater than 0 and less than 0. So I want to know when is it actually equal to 0 so that I can tell stuff about it. So if we take and set this thing equal to 0 and solve for x, we get negative 3 over 2 equals ln of x. And that means that x is equal to e to the negative 3/2 here. So this would be the place where we would expect to change concavity, if at all. So again, I'll set it up sort of the same idea as we had before, where we've got these number lines, and I have 0 as my starting point because remember, ln, our original function up here, has a domain of greater than 0, so nothing less than 0 is even defined. And we can kind of split it into these two intervals. And again, we can sort of look at our function or our f double prime. And all we care about is whether it's positive or negative on those two intervals. So if we look at that, well, ln of x is something that's always increasing. So if it's 0 at this point, then that means it's going to have to be negative at this point. And that means it's going to be positive over on this side as well, just because this function is actually always increasing based on how it's defined. And you could pick test points in between here as well to figure that out. I didn't want to do that here. So let's go ahead and look at this graph and see what we can see based on this information. So if we look at the graph right now, it doesn't look like I actually have any concavity switching here. It looks sort of, if we just look over here, that it's always just going to be concave up. But we have to zoom in a little to see what's happening here. And if we look very subtly, as we look near 0 here, we can see that it is actually going to be concave downward for a little bit. And that's actually what we've just sort of indicated. So the point that I said was e to the negative 3/2. So let's put that point in here and look at what happens. So when we look, this point, this e to the negative 3/2, when x is equal to that, it looks like we're switching concavity there. And if we keep zooming in, we can see that that is actually the case here. If I drew a tangent line in any of these spots over here, it is going to be above the actual graph, making the concavity downward. And that is seen when we said that the second derivative was negative in those different values. Then, once we hit that point, it switches, and now all of the tangents would be below the actual graph, making our graph concave upward. And again, that is seen when we look at this information that we gathered from the second derivatives here. So this type of point where we switch concavity gets a special name that we'll bring up now. So we'll say that a point P on y equals f of x is an inflection point if f is continuous there and the concavity changes as well. So the point that we had in our last graph that we showed would be an inflection point in this graph. Let's look at another example that we were working with last time in a previous video, where we were looking at g of x is equal to 4x cubed plus 3x squared minus 6x plus 1. And let's find the intervals of concavity for this one. So we took the first derivative, and it's easy enough that we can just do it again here, and we get 12x squared plus 6x minus 6. And then we can take the derivative again, and we get 24x plus 6. So if I want to find these possible points of inflection, I go ahead and I set this thing equal to 0 and solve for x, and we get x is going to equal negative 1/4. So that tells me that if I want to check concavity, I need to check the values to the left and to the right of this negative 1/4. So if I want to check something to the left as a test point, maybe negative 1 is a good choice. So g double prime of negative 1 is going to be 24 times negative 1 plus 6, and I get negative 18. So over here, it's going to be negative. So that tells me it's going to be concave downward. And then on the other side, if I want to pick a point here, again, maybe 0 is convenient because it's occurring over there. And so, you pick 0 here, and then g double prime of 0. Well, that's pretty easy. We just get 6. And so over here, it's going to be positive. So that tells me that we're going to be concave down from negative infinity to negative 1/4. and we're going to be concave up from -1/4 to infinity. And again, all I'm doing is looking at the sign of these second derivative. And let's go ahead and graph this and see what this is going to look like for us. And again, if we look at our graph here, we can see that if we put in any of the tangent lines over on this part of the graph, the tangent is going to be above the graph, meaning that we are concave down. And we can also just sort of see that from the shape here. And then at some point over on the right here, it switches. And that point where it switches, what we call the inflection point of going from concave up to concave down, happens right at that -1/4 spot, right, that we found right there. And from on the left, it's concave down, and on the right, it becomes concave upward. And so again, we can get information about the graph of this function without having to actually plot a whole bunch of different points. We can just use calculus to help us determine some of these things.